In this lecture, we will discuss magnetic force.
Most visible in the darkness of night, legend suggests that these bright dancing lights might be spirits, omens, or dragons in the sky. Known as Aurora Borealis in the north and Aurora Australis in the south, this colorful exhibition is actually the result of collisions between charged particles from the sun and atoms that they encounter as they enter the Earth's atmosphere. Disturbances associated with magnetism in sunspot regions, called coronal mass ejections or solar flares, allow free electrons, protons, and alpha particles to boil off into space in all directions from the sun, forming the solar wind. Most of the solar wind-charged particles reaching Earth are deflected by Earth's magnetosphere. However, near the polar regions, because of the geometry of the Earth's magnetic field, they spiral into Earth's atmosphere due to the magnetic force that acts on a charged particle moving through a magnetic field. The direction of that force can be found using the right-hand rule. The magnetic force can be computed from when these charged particles strike atoms in Earth's atmosphere, they cause electrons in the atoms to move to a higher energy state. When the electrons drop back to a lower energy state, they release photons, small bursts of energy in the form of light. And the night sky becomes a canvas painted with glowing lights. The colors created depend on which gas is being excited by the charged particles and on how much energy is being exchanged. Whether you're enticed by legend or by curiosity, the auroras are a spectacular sight to behold.
The direction of magnetic force is always perpendicular to both the velocity of the particle and the direction of the magnetic field. In this example, there are two possible directions that are perpendicular to both V and B, which is direction up and down. So we need to have a way to decide which is the direction of the magnetic force if we know what's the direction of V of the particle and B of the magnetic field. So let's assume we have a positive test particle. We can use our right-hand rule to find out what's the direction of magnetic force. There are several ways people can use to use the right-hand rule to find the magnetic force, but the one I like the most is the following. First, I point my forefingers in the direction of velocity, and then curve my forefingers into direction of magnetic field. Because I want to curve my forefingers into direction of magnetic field, so my palm has to be facing out. My palm has to be facing myself. So I can have my forefingers pointing in V first, and then curving to B, and then the thumb. My thumb will give me the direction of magnetic force. Now, what's going to happen if a negative charge moving in the same direction as shown? So we'll still use this right-hand rule. We'll put our forefingers in the direction of negative charge moving, curving into B, my thumb will be pointing up. Now, I just need to remember the direction of magnetic force on negative charge is in the opposite direction of my thumb.
Hi, I'm Dr. Bruce DiNardo here in the physics department of the Naval Postgraduate School in Monterey, California. When a charged particle moves through a magnetic field, a force on the particle can occur. This is the fundamental magnetic force. In this video, we will present a demonstration of the effect. In other videos, we will use the concept of the magnetic force to explain other demonstrations, including a jumping wire and a loudspeaker. This is a cathode ray tube, which produces a beam of electrons. The beam is visible due to argon gas in the tube. The electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. the beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal outward. When the magnetic field points to the right, the beam bends downward. When we switch the magnetic field, switch the direction of the magnetic field, the beam bends upward. When the magnetic field is pointing straight down, the beam bends to the left. But it has to do that because we can get back to our original case by just rotating the magnetic field. That's where we started from, the beam bending downward. Finally, when the magnetic field and the beam are parallel, there's no deflection. There's no magnetic force. The fundamental magnetic force law quantitatively accounts for our observations. The force is the charge times the vector or cross product of the velocity and the magnetic field. The force is perpendicular to both the velocity and the magnetic field, and the direction is given by the right-hand rule. The force is a maximum when the velocity and magnetic field are perpendicular to each other, and it is zero when they are parallel. Let's check the magnetic force law for the cathode ray tube in the case where the magnetic field points to the right. The velocity is this way, the magnetic field is this way, the force should be up. I bring the magnetic field in, and we see that the force is not up, it's down. So what's wrong? Electrons have negative charge, which flips the direction of the force. So the magnetic force law does work here. A charged particle that is moving in a magnetic field can experience a force, which is the fundamental magnetic force. The force is given in general by the charge of the particle times the vector product of the particle's velocity and the magnetic field. What if we have the common situation of a wire that is carrying an electric current? If the wire is in a magnetic field, there will in general be a force on the moving charges and thus a force on the wire. This leads to many demonstrations and applications. We will show some of these in other videos. It is important to remember that the physics behind these observations comes from the fundamental magnetic force law, which can be demonstrated by a cathode ray tube and a magnet. Physics lecture demonstrations are always fascinating, and the quest for them never ends. This is the Physics Department of the Naval Postgraduate School, and I'm Dr. Bruce DiNardo. Thank you.
Not only one moving charge inside the magnetic field can receive magnetic force. So if we have a bunch of particles moving, which give us current, so you can imagine it will give us magnetic force on that current as well. Let's see a demonstration of magnetic force on current carrying wire. We have a battery. We have a switch. This is a two-way switch. We have a wire and the magnets. Let's complete the circuit. We turn the switch in this direction, which gave us current in one direction. Then we turn it to the other direction, which flips the current. So the force flip as well. The current is a collection of many charged particles in motion. Since a charged particle in motion would receive magnetic force, so the current must receive magnetic force on those collection of charged particles in motion as well. So a force would be applied on a current carrying wire placed in magnetic field, as we just saw. The direction of the force is given by right-hand rule as well. All we need to do by switching from one particle to current is that we need to point our forefingers in the direction of current instead of pointing in the direction of particle velocity, positive particle velocity, which makes sense because the direction of positive particle moving gives us the direction of current. Now, we often use cross and a dot to represent the direction of magnetic field because it's 3D. So we have to have some way to represent what would be the direction of a magnetic field in and out of the surface. Cross would indicate the magnetic field B is directed into the page. And if we use dots, it will be indicated the magnetic field is directed out of the page. And dot would be represents the head of the arrow. If there's no current, there would be no force. If there's a current goes up, so let's test our right-hand rule, please. So first we need to point our forefinger in the direction of current. Then our forefinger would be pointing up. And we need to curve our forefingers into direction of B. In this case, my B is pointing into the surface. So what I need to do, I need to have my palm facing the screen. So I would have my forefingers pointing in the current up first, curve into the screen, and my thumb would point into the left, which gives me the magnetic force and the current. If a current goes down, magnetic field is still pointing into the screen. What I need to do, my palm is still facing the screen. You might need to twist your body a little bit. The best you can do is turn your body to the right. And then you have your palm facing the screen. Your forefinger is pointing in the direction of I. You curve your forefingers to the direction of B. You will find your thumb pointing to the right. That's the direction of magnetic force. The magnitude of the magnetic force acting on a current is given by this equation, BIL. B is strength of magnetic field, I is strength of the current, L is the length of the wire, theta is the angle between B and I. If the current is parallel to the field, then the magnetic force on the wire is 0.